All right, so on Wednesday before our exam, we were finishing up our radical chapter and we talked about polymers. Polymers are, like I said, one of the biggest components of the chemical industry for organic chemists. And we talked about how you can predict the addition polymer that will result for various monomers. So we went over polyethylene, we went over polypropylene, polystyrene, polyvinyl chloride, and polytetrafluoroethylene, or Teflon. I did post an article from the New York Times all about Teflon and DuPont. If you are interested in reading about it, it's a really interesting read in terms of environmental chemistry. But we didn't really get into the nitty-gritty of the mechanism for these reactions. So let's go talk about the radical polymerization mechanism. And just like with any radical mechanism, what's the first step? Initiation. There's a variety of commercial initiators out there. Oftentimes, though, if you're in a lab setting, you just use a peroxide, and you can cleave this peroxide using heat or UV light. When you do this, you now get two alkoxide radicals with unpaired electrons coming off of them. Now, we can do something with these radicals, and let's take ethylene, for example. So I'm going to have the hydrogens coming off of here. What's typically the next step in a radical reaction? Propagation, but we have one intermediate step too. Yeah, the hydride or hydrogen abstraction. So in this case, we only have one type of hydrogen to abstract. And when we do this, oops, sorry, let's back up. This will actually do a radical addition to this pi bond, and then we'll have abstractions later. Sorry about that. So let's fill in all these hydrogens. There we go. So this is an addition to a pi bond, which results in this new radical forming on one side of the ethylene. It normally prefers to have the radical on the more substituted carbon, but in this case there's only one type of carbon for it to add on to, so we're going to get a primary radical. This is pretty unstable. So now we can do our propagation step. And I'm going to shorthand this and not draw out all of our hydrogens, just to keep things clean. So I'm just going to abbreviate this as that guy. All right, so now we've got our really unstable primary radical. And we've got more ethylene floating around in solution. All right, if we have more ethylene floating around in solution, we can do another addition to our pi bond. And we get another radical out. So we've added on two new carbons from another ethylene monomer. What do you think can happen next? Yeah, we can do it over and over and over again. That's why these are called propagation steps, is that they could theoretically go on forever. So we could have this radical pop over, attack the pi bond, form a new radical. And I'm not going to draw this going on forever because that would take too long. But we can write etc. And we end up with some sort of super long polymer chain. And I'm going to put a little n in brackets there. What does that n stand for? Yeah, it could be some imaginary number. It could be 50, it could be 1,000,000, it could be 1,000. It really comes down to how much ethylene is available in solution for this polymerization to occur. What's the third step? Termination. We've got a couple different routes for termination. We could have two of these radicals actually couple together. And terminate. And form a new carbon-carbon bond. Let's see. Oops. And if we do this, we just get one super long carbon chain with oxygen groups coming off the end. And I'm just going to abbreviate one big N group in there. So with polyethylene, you just basically end up with one super long carbon, or there's another possible route where we could just couple, with another alkoxide radical, and again, we'd form a super similar product just of a shorter chain length. So let me fill in these N groups here. And couple and couple. Does that make sense? Yep.
Yes, but does polyethylene end in OR groups?
Typically, it depends on the initiator used. So there are some functionalized plastics where they actually have special side chains coming off of them. It really depends on the specific industrial use of that plastic. So they've got hydrophobic polymers or hydrophilic polymers. They've got ones that have special functionality coming off the end to append groups that will prevent mold buildup or mildew or things like that. There's a whole big industrial.
So anything that has like a super long chain in the middle is a polyethylene.
Yeah, and in this case, it's considered a polyethylene because it's an unfunctionalized ethylene monomer. If we did switch it to something like propylene, then it would just be polypropylene. And we would have methyl groups coming off of each one of these carbons, right? Mm-hmm. Or every other carbon, I should say.
It doesn't matter like what's on the end?
No, it doesn't matter. Oftentimes you end up with the statistical distribution, so that N may be anywhere from, let's say, 100,000 to 150,000, and 90% of all the polymers will fall in that range. So it's a statistical distribution oftentimes. It's not a set number. All right, there is one side reaction that occurs. And it's a really important side reaction. So let's say I have this radical floating around in solution, and then I've got another big long polymer, and I'm going to draw this polymer like this with an N, and we've got hydrogens sticking off each end. Sorry, let me clean this up a little bit. So this is the middle of a polyethylene chain, right? We've just got this big long carbon backbone. The radical on the end there can actually do a hydrogen abstraction and pluck off one of these hydrogens. And when it does that, you now get a new radical that's formed off of the inside of one of these polymers. So let me just finish this guy. So now we've done a termination through a hydride abstraction. So if we look at it, this one's terminated. But we can continue doing addition reactions with this new radical that we formed. So if we have more ethylene floating around in solution, this could do addition reactions to that ethylene unit. We've got hydrogens here, 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 but now we've added 2 carbons on. And this can keep on doing more and more addition reactions like we saw with that propagation step. This is called crosslinking or branching of polymers. So in this case, we've got a branch coming off the center of one of those big, long polymers. You want me to scroll up or down? Like that direction? Why do you think branching is important? Yeah, it changes the properties a lot. So do you guys remember on Wednesday, I said if you look at the bottom of like a water bottle like Rachel has, it will say HDPE. What does that HD stand for? High density. And then we said there's also low density polyethylene. Low density polyethylene has different amounts of branching as high density polyethylene. So by controlling the amount of side linked chains coming off of our parent polymer, we can control the property of the plastic. It doesn't? What's in the triangle? Is it a 2?
No triangle. It's non-recyclable.
Costco makes non-recyclable water bottles? All right, we'll check it out after class. All right.
Oh no, it's on the side.
So cross-linking can be controlled via catalysis. And it can change the physical properties of the plastic. This becomes really important for a lot of commercial goods where you may want a plastic. In one case, it's really, really rigid and strong. Other cases, you might not want it to be rigid because that makes it brittle. You may want it to be somewhat flexible. So you may have to explore various types of plastics and various amounts of cross-linking within those plastics. Yep?
Doesn't that make where it gets cross-linked like a stereo center?
Yeah, and it can be really, really hard to control. Like I said, when you go through this radical, let's even highlight it right here. That radical is trigonal planar. So you could have addition to the top side of that radical or the bottom side. And so you're going to get a mixture of products out of it. It's impossible to control, really. All right, I have some good news regarding Chapter 11. It's due tomorrow for sapling. Some people were worried that they were going to try to cram it in hours after class ended tonight. I'll give you guys an extra day since I want you guys to slow down and try to really conceptualize all of the various steps for initiation, propagation, and termination. So I gave you guys an extra day to work on it. Sound good? Yep.
So, putting it in brackets like that and throwing an N on the side of it, wouldn't that indicate that the branching happens for every single step?
So the question was, if you put brackets around here, does it happen at every single step for cross-linking?
Yeah.
Yeah, it could occur at multiple different sites within the polymer. So you could have branching only once in one giant polymer chain. You could have it occur every 5 to 10 units. You could have it occur almost every unit. It really comes down to how well you're controlling the cross-linking.
How would you write that as far as it being one unit versus another unit?
That gets into trickier chemistry and kind of outside the scope of this course. So at least right now, I want you to know the elementary steps for radical addition. We aren't going to cover all of Chapter 11 in terms of the biochemistry. However, if you are interested in biochemistry, I would really recommend that you read through those sections. They're pretty interesting, but we just simply don't have enough time this term to cover it in much detail. All right, next chapter.
Ready?
Yep.